Okay, so welcome everyone to another LEAP seminar. And today it's with great pleasure that we have Marco van Leeuwen, the senior scientist at the National Institute for Subatomic Physics, NIKHEF, at the Netherlands. So his PhD was focused on the study of the Quark Gluon Plasma, namely on strangeness and charge production measurements in heavy ion collisions at the NEA 49 experiment at CERN. After his PhD, he became a postdoc at the Lawrence Berkeley National Laboratory and the STAR experiments, where he started working on high PT physics and the study of parton and results in the Quark Gluon Plasma. Afterwards, he moved to the Netherlands and he has been working since 2007 on the LHC experiments, basically on jets and high PT physics related to Quark Gluon Plasma studies. So until now, Marco has delivered a lot of phenomenological papers as well that I highly recommend people interested in taking a look at. He's currently one of the upgrades coordinators of the ALICE experiment and has been elected as a spokesperson of the ALICE starting into 2023. So I don't think that we could have a better person to talk today about the study of the Quark Gluon Plasma with the ALICE detector at the LHC. So Marco, please start whenever you want.
Thank you for the introduction, Liliana, and thanks everybody for attending. Let me just check with the mouse pointer that
We can see your slides.
Yeah, I wanted to try and make the mouse pointer visible, but this is always a bit of a struggle. Maybe because Keynote has something, but it's
now, yes,
okay.
Yes, we can see. Thanks.
Good. Okay, so yeah, I would like to walk you through some of the most interesting results of the study of the Quark Gluon Plasma with heavy ion collisions at the LHC, and I'll really focus on ALICE because that's what I'm familiar with, and I also didn't want to put too much in, and I'll also try to give actually quite a bit of the time will be spent on outlook for the upcoming run and future upgrades of the experiment. But of course, all of that with a focus on the physics and the understanding of the processes. So before going into the physics, I would like to sketch a little bit the experimental situation from the ALICE perspective. So on this slide, you see the timeline of the LHC and with some annotations for the situation in ALICE. The ALICE detector has just been upgraded. We are now starting, as you probably know, the run 3 of the LHC. So the cavern has been closed now and all of our upgrades are installed. And this was really a major overhaul of the experiment, with the main features being that we increase the interaction rate or the data collection rate by a factor 50 to 100. And we also improve the pointing resolution. I'll show later on what the impact of that is on some of the measurements. And as I mentioned, the beams are now really imminent. So we already took some actually pilot beam data last year as part of our commissioning. And we're really eager to get going with the experiment. And the first heavy ion run will be at the end of this year. First heavy ion run of run 3. Now and then, after 4 years, there will be another long shutdown where the other experiments do their main upgrades. And there we will also perform some upgrades called ITS3 and the forward calorimeter, which I'll introduce in a second. And then after another 4 years, there will be another long shutdown, and we've just developed plans for a complete overhaul of ALICE for that period, and that is called ALICE3, and I'll also explain that to you. So now to start from the upgrades that we've just installed, so you see here a sketch of the ALICE detector in the middle. Of course, with the beam lines and all the detection elements around the beam. You also see the forward muon arm, the blue magnet and the planes in the forward direction. Now, the whole experiment has been upgraded to be able to collect a larger interaction rate. And that has also led to the installation of this online event processing farm at the experiment, which you see in the lower right corner. For the other detectors, so the ITS, the inner tracking system, has been completely replaced. You see a photo here of the new detector, which is completely based on pixel detectors. And that improves the spatial resolution compared to the previous inner tracking system. And it also works at a higher readout rate. The other major one of the other major upgrades is that in the TPC, the time projection chamber, which is around the inner tracking system, we have replaced the readout chambers with so-called gem foils. And that allows us then to take higher rates of events with the TPC where space charges are concerned. And then the fast interaction trigger is depicted here, which are trigger detectors to tag collisions in the experiment, which have also been upgraded. This is not the whole package, but these are kind of the highlights of what has been really completely renewed and replaced. Now, as I mentioned, so this is all ready to take data, and then we have 2 more upgrades planned for the next long shutdown. So this is where really active work and development is ongoing. One is sketched here on the left. This is called ITS3, where we plan to replace the inner layers of the inner tracking system and the beam pipe with fully cylindrical tracking layers. So you see here a diagram and also a mock-up, a mechanical mock-up of what this looks like. So these bent layers here are really silicon wafers, not yet instrumented with sensors in this case, but you can see that if you make silicon very thin, you can get this very nice cylindrical detection layers. And this is now under development, and that will improve the performance for heavy flavor reconstruction and for Di-lepton measurements, which I will explain later in the talk. And the other upgrade for that long shutdown is the forward calorimeter, which is a high granularity calorimeter, which is mainly for photon detection. And it's a high granularity calorimeter. You can see here on the right, you see a kind of a shower event display where there are elements that have a 1 square centimeter size. Those are the big boxes. And then there are pixel layers interspersed, which are very fine granularity to be able to identify photons from pi-0 decay. So this event display has 2, the red and the blue are 2 photons that give separate showers, which can be distinguished in this detector. And that is important for small x physics and also for measurements of pi-zeros in the forward direction in lead-lead collisions. Now I'll present more of why you want to do all these things throughout the talk, of course. Now, before going to the physics, then the last upgrade or the next phase that we foresee is LS3, which is for run 5 and 6. So this is to be installed in basically 10 years from now. Now this is a completely new detector, completely replacing the current setup with a silicon tracker with a very high resolution vertex detector that is actually placed inside the beam pipe to improve the pointing resolution by a significant factor. And then that is supplemented with particle identification systems for hadrons as well as electrons and muons. And to get an impression for how that evolves the experimental capabilities here, there is a sketch where you see the acceptance times interaction rate on one axis and the pointing resolution on the other axis. And you see that every time we make significant steps. So from the previous setup to now, we have an increase in both interaction rate and pointing resolution. Then with ITS3, the pointing resolution improves further. And with LS3, we make another step in both of these coordinates. Okay, so with that kind of introduction on the experimental setups and plans, I will now switch to the physics discussion. And to start, I would like to show you this animation of a heavy ion collision. This is, of course, not a measurement, but really a simulation. And I would like to use that to introduce to you how we think about the evolution of a heavy ion collision. So what you see here are 2 nuclei, a red and a blue one, and they're not spheres but pancakes because of the Lorentz contraction. So they come into the system from the left and the right. If I start a movie, you will see them move closer together. And then you will see that the calculation switches to a fluid description, which are these color lines. So this is, in this calculation, we transition to a QGP fluid, and then the system keeps expanding and cooling down. And now you see that hadrons have been formed and are flying out towards the detector. So, we see 3 stages: the initial stages before the collision happens, Then there is a stage of thermalization, equilibration, and then there is a fluid expansion stage, and then hadrons are formed. And this fluid is, of course, the little bang that we want to investigate, which recreates primordial QGP matter in the laboratory. Now, in the rest of the talk, I'll give you some sense of what we can study and what we know about this Quark Gluon plasma, and maybe also some places where there are experimental difficulties or mechanisms that are a bit maybe confusing, and try to give you a sense for where we are with that. So one of the ways that we can study the plasma is by looking at the azimuthal anisotropy. And this is an effect that you measure in the final state, but originates from the initial state. And to explain that, you see here a sketch of the two nuclei as they collide. So this is a beam view. The nuclei are moving in and out of the screen. And if you have a non-central collision, there's an overlap area which is approximately elliptical. But I say approximately because, of course, in reality, there are nucleons inside the nucleus. So there are protons and neutrons, which give a non-uniform structure to this collision zone. And this is a Monte Carlo simulation of a single event. And it shows that even though you have a dominantly elliptic shape, due to individual fluctuations of the distribution of these nucleons in the nucleus, you get quite irregular shapes. And these shapes you can characterize with azimuthal harmonics. And I sketched that here. So this is the first, or the second harmonic, the elliptic harmonic, which is referred to as V2 or epsilon 2 for the spatial one. But there are higher harmonics. So there is a third harmonic, the green one, and a fourth harmonic, the red one. And this is actually, the amplitudes here are representative of a real expansion of this azimuthal distribution space as a function of the for this specific event. Now, then what happens is that this is the initial density profile, sketched here again for a slightly different collision, but more in a continuous way. And what happens is this is in vacuum, so it starts expanding. And because it's an irregular shape, it expands in all directions, but not at all directions in the same rate. And that leads to a non-uniform azimuthal expansion. And one of the key parameters of the Quark Gluon plasma that plays a role that affects this expansion is the viscosity. And that I want to illustrate here. So if there is no or zero viscosity, then the expansion, though this is from a hydrodynamical calculation, the expansion after a while looks like here shown on the upper right. And what you see is that this kind of very irregular pattern, it changes, but it stays very irregular. So because there's no viscosity, there's no smoothing out of the density profile. Instead, if you have viscosity, you get a pattern like this, which is starting from the same initial condition, but you see that it becomes more spherical or elliptical. So the viscosity really affects how these irregularities propagate from the initial state to the final state that you can measure in the end. Now, to show you how we measure this, I have two illustrations. So this is, again, for reference, this initial state picture. And then on the right, you now see measurement results. So on the top, you see the azimuthal distribution. So this is the angle around the beam of all particles in a single event. And you see here that there is a significant modulation of this azimuthal distribution. And you can actually fit it with this harmonic expansion. So the red, green, and blue are a second and third order harmonic, and there's even the fourth, I think, fitted to this distribution. So already at the single event level, you see these anisotropies, but to measure them accurately, what you do is you sum over many events, and that is what you see at the bottom. And then you get such a profile where now you can very clearly see all the harmonics, and you can extract even up to sixth harmonic from this data. Now, numerically, the way the analysis proceeds is slightly different, but this is really a good way to illustrate these harmonics and how visible they are in the final state. Now, and then just to give you an idea, what we do is we have measured this for many particles. And in Alice, we have an array of particle identification detectors, so we can measure this for pion scales and protons, and also for strange particles, and I'll show later for heavy flavors. And this shows the elliptic flow as a function of PT. And you see here in particular that at low PT, there's a kind of pattern that the higher mass particles have showing a V2 at higher PT. And that is a signature of a collective expansion velocity, which can again be calculated much more accurately with a hydrodynamical model. But I want to just give you here the qualitative feel for what to look at in the data. In the middle, as a curiosity, I show that we also measure the same effect for nuclei. So there are the deuterons, the red points are deuterons and antideuterons, and they show the same V2, and they follow actually the same mass scaling that we see for the other particles. And then one can also measure the higher harmonics like V3 and V4, and just wanted to give you a sample here of what these data look like. Now, and then what we can do with this is we can extract the viscosity from a sample of these data. And this is something that has been developed in much more detail recently. Our multi-dimensional, multi-parameter fits to a global data set. And I want to, for this case, I show you the result later. I'll show you a bit more in detail how this works. So this is then the extracted viscosity as a function of the temperature of the Quark Gluon plasma. So you see the temperature scales goes from about 150 MeV, which is the phase transition temperature to the Quark Gluon plasma. This is about 10 to the 12 Kelvin, to 300 MeV for this particular model. And the gray band is a prior range. So this is the range of viscosities that was explored in the fit. And then the blue band shows the viscosity that is in agreement with what with the measurements. And you see that the value, we normally plot eta over S over the entropy density, that is to make a dimensionless quantity that scales well. And you see that is the value is about 0.1 at the phase transition temperature, and then it slowly goes up. And we are now with these data sensitive to even to the temperature dependence of the viscosity. Now, is this what you expect? To think about that, one can compare to other liquids, such as water or nitrogen or even helium near its superfluid phase transition. And you see here that all these materials, they have the characteristic behavior that below the phase transition, the viscosity decreases and then it increases again. But the values of this eta over S are much larger, even for superfluid helium. And the Quark Gluon plasma sits here at the very low end, is actually very close to the quantum mechanical ADS-CFT bound, which is the value below which you cannot go with the viscosity due to basically the uncertainty principle. So this is quite a spectacular result, because it shows that the Quark Gluon plasma really behaves as a almost inviscid fluid with a viscosity that is close to the lower bound. Now, there are other ways to investigate the Quark Gluon plasma, other properties that we can determine. So I will switch now to those. So what I've just introduced is a way of looking at the plasma by looking at the final state particles that are really produced as the plasma cools down. And this is what we normally refer to as soft probes. And the Azimuthal anisotropy have explained, one can also measure light flavor particle ratio, so the amount of different particles. And thermal radiation, I'll come back to that towards the end, which is really a direct probe of the initial state temperature. But before going there, I wanted to discuss a little bit more what we call hard probes. So these are hard processes that take place in the initial state of the collision, and then partons, light and heavy flavor partons, they propagate out of the plasma, and as they do that, they radiate and lose energy. And these are attractive processes because the initial production process can be calculated with perturbative QCD or measured in PP collisions. And then you can look at the modifications of these processes. And in particular for heavy quarks, you have an additional feature that is that the charm and beauty, the amount of charm and beauty is preserved throughout the collision history. So there's not much change in the strong interaction of you cannot generate at the thermal scales new charm and beauty quarks. So that you really can kind of trace from the production to the final measurement what happened to the charm quark. So I'll focus today on the heavy flavors, but would also like to introduce some of the light flavor measurements. So let's start from there. So how do we characterize this? So one way is using the nuclear modification factor, which is basically a measurement of the PT spectra, which you see here at the left. So these are PT spectra measured in PP collisions and in lead collisions at the LHC, and you see here that all the different experiments agree very nicely. There is, of course, on the vertical axis, there's a normalization factor that takes into account the fact that in lead you have much more nucleons than in PP. And you see that when you compare the two, the lead results are below the PP results, or better, if you think of energy loss, what actually we think happens is that the the production processes that take place in PP take place in lead as well, but then the partons that propagate through the plasma, they lose energy, so the spectrum shifts to the left, as it were. And that is indicated here by this green arrow, but normally when we look at these data, what we actually plot is the ratio of these two spectra, and that is the nuclear modification factor. So there, this shift to the left, it translates into a ratio that is below 1, which you can see here on the right. So this is really the ratio of the red and blue spectrum. You see that at high PT, there is a suppression. The ratio is below 1 due to energy loss. And then at low PT, there is this pattern which is actually related to the elliptic flow that I just discussed. So this is here soft production processes dominate, and this is so you cannot model it with a simple picture of production and then subsequent energy loss. Now we can do the same measurements for heavy flavor. So these I compare here. So on the left you see the light flavor measurement. This is basically the same data as you saw on the previous slide, but now for charged pions and charged hadrons. And there are some model curves drawn in addition. I'll discuss that a little bit more later. And you see on the right the same measurement for D mesons. And you see that there's actually very similar behavior. So even the charm quarks that then hadronize into D mesons show this behavior that at high PT there is a suppression due to energy loss. I just wanted to point out that in the case of heavy flavor, D mesons, this peak at low momentum, it also probably has to do with elliptic flow, but it's also important to realize that because the charm content is conserved, if you have a suppression somewhere, you have to have an enhancement or at least no suppression somewhere else. So that is exactly what you see here at low PT. Now then, before going to the model discussion, I wanted to point out that also here we can measure the azimuthal anisotropies. And here the way to think about azimuthal anisotropy is a little bit different. So here on the right, you see the measurement of the D meson, so the charm meson V2 as a function of PT. And these values that you see here of about 0.15 or 0.1 at high PT, these are actually not so different from the light flavor case. But here we really have a case where, as I mentioned, the charm is produced in hard scattering initially and anisotropically. And then there's energy loss, which is different if you have a non-central collision with an elliptic overlap zone as sketched here. The energy loss is less in the horizontal direction in the sketch than in the vertical direction, where you have a longer path length, a longer mean path length. And that gives rise then, that produces a similar anisotropy. So here the anisotropy is really created by interactions with the plasma. instead of by the freezing out of a fluid element. And so for heavy flavor, this effect is purely generated by interactions. If there would be no interactions, you would expect no azimuthal anisotropy. So here we can also do a similar exercise like I showed before. We can take the data, and here's from a particular paper I show what they did. So they took different measurements from the LHC, the nuclear modification factor on the left, the V2 on the right from CMS in this case, and then you run your model several times with different parameters, and you get a spread of the curves, and then to determine the physical parameters, you compare all these curves and you retain the ones that fit the data, and that is what you see here, that is done here. It's from the same paper. Those are the curves that are in agreement with the measurement, and that leads then to a range of model settings that agree with the data. And there are several model parameters, and the physical parameters that we're most interested in are the transport coefficient. So you see them here. On the left is the diffusion coefficient, which is actually the spatial diffusion coefficient, which characterizes elastic energy loss mostly at low PT. And the red band is the range that was extracted from the data that I just showed you in the way I just showed you. And this is in good agreement with expectations from lattice QCD calculations, which are shown here at the bottom. By the points, in fact. So the circles and the stars are different lattice QCD calculations. You can see that there is still some uncertainty in exactly how to calculate this on the lattice. And there's also still a sizable uncertainty on the data, but they at least are close together, which is encouraging. And then on the right, you see the other high PT transport coefficient, which is a measure of the amount of kind of transverse scattering as a parton propagates through the Quark Gluon plasma, the mean Q per mean free path. And again, you see in this case, just the data constraints in red, and then there are a few other theory calculations and also other fits to the data. So what is emerging is really a very consistent picture of this heavy flavor and light flavor transport with these transport coefficients. But some questions remain, and this will be also part, of course, of the things we will address in the future. And I'm trying to highlight some of these questions here. So one of the open questions to my mind is the interplay or the relation between these two transport coefficients and the underlying processes that I just showed you. So one is the diffusion drag coefficient, which is related to elastic processes, which we know or which we think are dominant at low PT. Well, on the other hand, we also expect to have inelastic processes, gluon radiation, which are more determined by this Q hat coefficient and which are dominant at high PT. And you have, in fact, here on the right, just to illustrate these points, I show you a comparison of models with different settings, and you see, for example, the green here without radiative energy loss. It differs most at high PT. And the other set of questions is more related to the approach to thermalization. So, as I mentioned, this V2 of the D mesons is actually fairly large. It's close to what we see for light flavor. So that seems to suggest that charm already is close to thermalized. When it goes to the plasma, it completely loses its memory of the initial state. And we expect this effect to be much smaller for beauty. And so it will be interesting to measure for beauty and to really test this mass dependence and momentum dependence of the transport coefficients. And one more thing is the role of hadronization, which is when we relate the D meson V2 here to charm quark V2, there's the question whether the light flavor V2 also comes into play, and that would go via coalescence. So if a D meson contains a light and a heavy quark, and the light quark, if it flows that flow might also be reflected in the D meson V2. And that is something that, that we think plays a role, but that we want to understand more quantitatively in the future. For example, by measuring baryons, where you have 3 quarks, so you have actually a stronger coalescence contribution. And this is just to show is one example of the future performance. So this is for the upcoming run, the light gray, and then run 4, the dark gray, and LS3 is then the far future experiment, where you see our capability to measure the V2, the Azimuthal anisotropy for lambda C, so the charm baryons, and for lambda B, the beauty baryons. And you see that in the coming time, we will make progressive steps towards measuring this very accurately, which then will allow us to disentangle the various effects of charm and beauty transport, and also the contribution of hadronization. Now, there's another way to go after hadronization, which is even in a way more spectacular. So just to tell you again why we think this is so important, I show here an existing measurement of the lambda C to D meson ratio, so the charm baryon to meson ratio, which is, you see here as a function of PT, is about 0.5 at low PT and then goes down a little bit. And measurement or models that are tuned to E+, E- give a much lower measurement, much lower value. It's about 0.1. So we already see that in PP and AA collisions, the baryon production is enhanced with respect to E+, E-. And that led to some of the discussion about the V2 that I already told you about. Now, one way to make even more progress in this would be to measure multi-charm baryons. In particular, if you have a triple charm state, you know that all the charm quarks have to be produced in the initial hard scattering, and that the only way basically to form such a state is by that the charm quarks find each other in the final state. And that leads to a very large enhancement of the yield. So what is shown here are the yields of double and triple charm baryons as a function of mass of the colliding system. These are all model calculations because we don't have yield measurements yet. And you see that the expected increase is about a factor 100 for double charm and a factor 1000 for triple charm. So this is very sensitive to these types of processes, and it's very clean because charm quarks are conserved, as I mentioned. And the way we can go after that is by a new technique which we call strangeness tracking, and this is mostly is being explored both for run 3 and 4, but will probably come really into its own for the LS3 experiment. I just wanted to show you briefly what it looks like. So some of these double charm baryons, like the Xi-CC, they decay into a single charm baryon, which then decays into a single strange Xi baryon. And this Xi baryon is charged, so it can be tracked in a tracker. And you see here an event display where you have a Xi, so a strange baryon, flying and hitting 4 of the tracking layers before it decays into a lambda and a pi meson, which can be reconstructed. And the nice feature of this is that these Xi baryons are relatively rare. And with this tracking, you can then point back to the primary vertex and you can look for secondary, so Xi's which come from decays. And then one of the main decay candidates or mother particle candidates is the Xi-C or the Xi-CC. And that really turns out to be a great help to reduce the backgrounds and to make these type of measurements possible. And then here you see a projection of how accurately we can measure that with the LS3 setup for the double charm baryons. So you see here projected measurement, and you see that both in PP and in LED this is achievable in that setup. Now, this was a bit of a detour towards the hadronization. I want to come briefly back to this energy loss process. Because one signature that you may have seen before in other talks is the dijet signature, and also how this is sensitive to energy loss. So dijets are shown here, or jets and dijets are shown here in 2 event displays. we normally have as coordinates, we use eta, which is the longitudinal direction, and phi, which is the azimuthal direction. You see that better in the left picture. And then you see that even though you have a lot of particles in an event, if you measure the transverse momentum, you see clearly sticking out this peak here on the upper left and the two red peaks in the right panel, which are jets, which are signatures of high momentum partons, quarks or gluons, which fragment and hadronize. And the interesting thing is that here on the right, you also see that the two jets are not balancing in transverse momentum. And that is very unusual. In PP, they would balance or approximately balance. And that means that interactions here have softened the second jet and redistributed its momentum throughout the plasma. Here I show again this display, and then on the right you see how we normally quantify this. For example, by plotting the ratio of the PT of the second jet over the first jet. So if this ratio is 1, then you have a perfect momentum balance. And in PP, you see that the distribution is peaked towards 1. So there are, of course, fluctuations around that. But in lead-lead collisions, there's a clear shift of this whole peak to lower values, which is due to these interactions with the plasma. Now, this measurement is a very direct probe of the lost energy. I mean, in a naive picture here in this display, you would have lost 130 GeV into the plasma by interaction. So these are really large effects. You can also measure not only the longitudinal loss, but the transverse kicks of these processes, and that is also something what one can also do with DD bar azimuthal correlation. So charm quarks are produced in pairs, CC bar, and they give then rise to a pair of D mesons. And also for this process, so this process is interesting because you again have a final state signature of the initial state quarks. And with this signature, you can actually go down to very low PT, which makes it very sensitive to transverse broadening, so directly to the propagation or the diffusion through the plasma. And again, there with LS3, we can measure this process with a good precision, as shown here. This is again a projection, and this is a very challenging measurement. It really needs a very good purity of the signal. So we also looked at how well we could do this for the upcoming run 3 and 4, but the result is rather disappointing, as you can see. So it's really, the backgrounds are so large that to do this, you really need a very good tracker to be able to do the DD bar correlations and measure this transverse scattering. Now, this is what I wanted to say about energy loss and about interactions with the plasma and hadronisation. Now switch to the thermal signatures, where we look at electromagnetic particle production. And one of the measurements that we've done is direct photons. So the idea here is that at low PT in particular, photons can be produced by thermal processes, just like the sun shines. Now this is easier said than done. If you measure photons, there are very large backgrounds from pi zeros and from eta decays, which all have decays to 2 photons. And what you see here on the right is a bit of a technical plot, but it's the ratio of the total photon yield to the expected background from the decays. And as you can see here at low PT in particular, the excess above the expected decay background is very small. And then at higher PT, it starts to rise. And there are 2 types of production processes. So at high PT, there's the Quark Gluon Compton process. So hard scattering produces photons directly. And that is what's actually shown by the black line. That's the recalculation for this process. And then at low PT, we expect that thermal radiation would be dominant if there is enough of it. And we see a small excess. So if you turn this now into photon spectra, this is the plot. And you see that for the more peripheral collisions, at low PT, we only have an upper limit. And then at high PT, we agree with the expected hard scattering contribution. And then if you go to more central, then in the most central bin, we have some signature of or some excess of direct photons. And in this plot, we have several curves of thermal production yield. So you can see that the measured yields are in agreement with the thermal production, but at the moment the precision is not good enough to really constrain them. Now, before continuing with the thermal production, I want to make one sidestep in this kind of more hard scattering processes, because the focal that I mentioned at the start, an upgrade for run 4, has the goal to measure direct photon production in that regime, in the hard scattering regime, and to use it to constrain the gluon density in the nucleus. And to give you a flavor of how that works, here on the left you see again this signal photon fraction, which is very small at forward rapidity, 10 to the minus 2, if you don't do any selections. But then with the forward calorimeter, you can do an isolation cut, and you can reject decay photons directly with this high granularity. You can bring the signal fraction up to above 10%, which then makes it possible to subtract the background and measure the direct photon yield accurately, which is shown here in the middle panel, where the blue points are the projected measurements uncertainty, or the blue band, and it's compared to the current uncertainties on theory on the nuclear PDFs. And then on the right, you see how that helps to constrain the nuclear PDFs. So the gray is the NN PDF 2.0, one of the nuclear PDFs that exist. And you see there that below 10 to the minus 4 in the momentum fraction X, there are very few constraints. And this data from the focal will help to constrain in the range 10 to the minus 5 to 10 to the minus 2. Now that was a bit of an aside on these hard scattering photons. And now if you want to go really look at the thermal production to study the plasma, it turns out that a good alternative, secondary method is to look at virtual photons. I'd like to briefly explain that. So virtual photons are E+ E- pairs in this case. And you see here the mass distribution of E+ E- pairs. And what's interesting to see is that this blue line shows the contribution from hadronic decays, including the by 0 eta and even some higher resonances. And you see that this contribution really dies out at about a mass of 1 GeV. So if you measure above 1 GeV, you have no hadronic decay background or very little, and you can measure mostly thermal processes. Although there is one hadronic decay background, which is actually the heavy flavor pair production background, and those are drawn here or sketched here, BB bar and DD bar. But the goal that we have for run 3 and 4 is to actually measure this and to extract the thermal yields. And to show you a little bit of how that works, so these are now, again, projection plots of performance for run 3 and 4 of the Di-lepton measurement with the current upgraded ITS and then the ITS3 upgrade. What you need here is really excellent particle identification, low material budget so that you don't have conversion backgrounds, and a very good pointing resolution to reject these heavy flavor backgrounds that I just showed you. And then you get a clean signal and you can fit at a high mass, you can fit the slope, and that slope is actually a direct measure of the temperature. And that is then shown here on the right is the expected precision of the measurements of the temperature in run 3 and 4. Now, this will be the first measurement, the first direct measurement of the initial stage temperature at the LHC, and it's something that will come up in the coming run. Now, for the future upgrades, we plan to make steps there by having a better pointing resolution and better identification capabilities. We can actually reject more of the heavy flavor background here at high mass. So that is shown by this solid and dashed pink lines. And that leads to an improved precision. So here we compare the precision of the Di-lepton mass spectrum in the thermal range between ITS3, so the current and near future upgrades, and LS3, the farther future upgrades. And then on the right, you see a projection of the mass spectrum. And one thing that is highlighted here on the right is the range where rho A1 mixing actually affects the spectrum, so where we are sensitive to chiral symmetry breaking. But then at even higher mass, we are sensitive to the temperature, as I mentioned, and with LS3, so the next upgrade, we can then measure things like azimuthal anisotropy of these thermally produced Di-leptons with high precision as a function of PT. So that then gives us access to the flow field before hadronization via the thermal emissions. So that is what I wanted to tell you. So I hope to have shown you that heavy ion collisions at the LHC really allow to study properties of bulk QCD of the Quark Gluon plasma. And in particular, I showed that we have a large azimuthal asymmetry for light and heavy flavors, and that means that the viscosity of the Quark Gluon plasma is very, very small, close to this lower bound. And that the heavy flavors have such strong interactions with the plasma that they approach thermalization, although we don't know exactly quantitatively how they are thermalized at the moment. And then with large, with high PT probes and heavy flavor at high PT, we measure these energy loss processes, which are lead to a large modification of the high PT yields. From radiative and collisional energy loss, and the transport properties that we've determined so far are in line with expectations from lattice QCD and perturbative QCD. And I also spent quite a bit of time on how we now proceed, what we expect for the upcoming run 3, and also what our plans are beyond run 3, both in terms of precision for these heavy flavor transport processes, for the hadronization measurements, and also for the first measurements of the temperature of the QGP before hadronization. Thanks for your attention.
Thank you, Marco, for these very nice overviews.